Hello everyone, welcome to my class. In my previous video, we talked about the spectrum. Now in this lecture, we will discuss Bohr's model for hydrogen atom. But before we proceed to the Bohr's model for hydrogen atom, the major limitation of Rutherford model was that Rutherford model was not able to explain that while moving an electron loses energy and ultimately it will come closer to the nucleus and electron will fall into the nucleus. So this main limitation was put forward by Bohr on the basis of Clark-Maxwell theory, which Rutherford was not able to explain. Now, in order to explain this limitation, Bohr proposed his model called Bohr's model for hydrogen atom. Niels Bohr in 1913 proposed a model which explains the features of hydrogen atom and its spectrum. His model is based on the following postulates. Number 1. Electrons in a hydrogen atom can move around the nucleus in a circular path that has a fixed radius and energy. These paths are arranged concentrically around the nucleus and are called orbits. The energy of an electron in orbit does not change with time. However, when the electron absorbs a required amount of energy, it moves from a lower stationary state to a higher stationary state. On the other hand, when the electron emits energy, it moves from higher stationary state to a lower stationary state. This energy change is not continuous and it appears in the form of a radiation having particular wavelength or frequency in the hydrogen spectrum. Now the following equation gives the frequency of radiation absorbed or emitted when an electron transitions between two stationary states take place, and those two stationary states differ in energy by delta E. So delta E is equal to, we can also express it in terms of frequency. So first of all in terms of frequency, that is nu is equal to delta E upon H, or nu is equal to E2 minus E1 upon H. What is E1 and what is E2? E1 is the energy of lower energy state and E2 is the energy of higher energy state. This equation is called Bohr's frequency rule. Now in a given stationary state, the angular momentum of the electron is given by mvr is equal to nh upon 2 pi, where n is always a whole number and its value starts from 1, 2, 3 and so on. So electron can only move in those orbits whose angular momentum is an integral multiple of h upon 2 pi. That is, there are only certain orbits which will be permissible. So hydrogen atom described by Bohr's model. Now for the hydrogen atom, Bohr theory describes that stationary states for the electrons are numbered n equals to 1, 2, 3. These are nothing, these are just called principal quantum numbers. Number 2, radii of the stationary states are given as Rn is equal to n square into A naught, where A naught is 52.9 picometers. Therefore, the radius of the first stationary state in Bohr's orbit is 52.9 picometers. It is the first stationary state, that is the first Bohr's orbit. So electron in the hydrogen atom is in this orbit, that is n equals to 1, because hydrogen has got atomic number 1 having only one electron. So initially it is present in the first shell. So it will be having, the first shell will be having the radius 52.9 picometers. As n increases, means as the number of shells increases, means electron shifts from 1 to 2, 2 to 3, 3 to 4. So when we talk about the radius of the fourth shell, as n increases, r will increase, radius will increase, and the electron will be found away from the nucleus. Now the energy of the stationary state is given by the equation En is equal to minus RH 1 upon n square, where RH is Rydberg's constant and n is any integer having value 1, 2, 3 and so on. For example, if we want to calculate the energy of hydrogen atom or when the electron is present in the second shell, so electron in the second shell, we have to simply use n is equal to 2. So En is equal to minus RH upon 2 square. That will give us the energy of electron in the second shell. Here RH Rydberg constant has got a definite value in terms of joules, that is 2.18 into 10 raised to the power minus 18 joules. So using this equation, we can calculate the energy of any stationary state. Next is, the energy of an electron is taken as 0 when it is not under the influence of the nucleus. In this situation, n is equal to infinity and the atoms are called an ionized hydrogen atom. Ionized. Bohr's theory is also applicable to ions with only one electron, means for hydrogen-like species. Hydrogen-like species, for example, He positive, Li 2 positive. He positive and Li 2 positive, both are having one electron only. So they are hydrogen-like species. So we can modify these formulas for hydrogen-like species by simply using atomic number. For example, the energy can be modified as En is equal to minus 2.18 into 10 raised to the power minus 18 z square upon n square, where z is the atomic number. So we have to take the square of the atomic number. And similarly, the radii equation can be modified. How? Rn is equal to 52.9 n square upon z. So 52.9 is the radius of first shell of hydrogen and z is the atomic number. Next is, what is the significance of negative sign for electronic energy? We have seen in the equation we are writing En equals to minus 2.18 into 10 raised to power minus 18 z square upon n square. So why the term is negative? We can also write the same equation as minus 1312 upon n square. Minus 1312 upon n square, and for hydrogen-like species minus 1312 z square upon n square. But what is the difference? Here we are using 2.18 into 10 to the power minus 18 unit of energy in terms of joules per atom. And when we multiply it with Avogadro number, it will become the joules per mole, which can be converted into kilojoules per mole. So when we convert it into kilojoules per mole, the another formula will become minus 1312 into z square upon n square. Here it is in kilojoules per mole. So we were discussing why the energy is negative. If we say that electron is very far away from the nucleus, it is at infinite distance from the nucleus, means it will not experience any attraction with the nucleus and hence its energy will be regarded as zero. Now as electron starts approaching the nucleus, means from infinity it starts moving towards the nucleus, then some force of attraction will start developing. When the attractive forces develop, some energy is always released out. So the energy less than 0 is called the negative energy. Since the energy of the electron will become less than 0, so the electronic energy is always written as the negative energy. Means it has a negative sign in an energy equation. After this, let us now come to the explanation for the simultaneous appear of many spectral lines in the hydrogen spectrum. So for that, before that, let us now complete one more equation, that is the velocity equation. Velocity, if we want to calculate the velocity of the electron in any particular shell, it can be calculated simply by using the equation Vn is equal to V0 into Z upon N, where V0 is the velocity of the electron in the ground state, means in the first shell, and that is 2.18 into 10 raised to power 6. So V0 has got the definite value 2.18 into 10 raised to power 6 meters per second into Z upon N, where Z is the atomic number and N is the number of shell in which electron is revolving. Now let us explain the line spectrum of hydrogen on the basis of Bohr's model. Bohr's model can explain the line spectrum of hydrogen atom because according to assumption 2, radiation is absorbed when an electron goes from orbit of lower energy to higher energy, whereas radiation is emitted when it moves from higher to lower orbit. Now the energy gap between the two orbits is delta E is equal to EF minus EI, where F is the final orbit or final shell, I is the initial orbit. So, since En equals to minus RH 1 upon n square, so we can say that delta E is equal to minus RH upon NF square minus RH upon Ni square, or simply RH is equal to 1 upon Ni square minus 1 upon Nf square. Here RH in terms of joules per atom is 2.18 into 10 raised to the power minus 18 joules per atom. And if we want to convert it into joules per mole, then we need to multiply it with the Avogadro number, that is 6.022 10 to power 23. Next is, after this, look at now this energy graph for the energy level for hydrogen atoms, different energy levels. Now in this case, if we simply substitute the value of N in the given formula, we will be able to calculate the energy of a particular orbit or particular shell. For example, we can directly use the formula minus 2.18 into 10 raised to the power minus 18 upon n square. Energy will come out to be in joules per atom. But if we are using the formula minus 1312 upon n square, energy will come out to be kilojoules per mole. For example, if I put n equals to 1, the energy of the first shell is minus 1312 upon 1 square is equal to minus 1312 kilojoules per mole. Put n equals to 2, it will be minus 1312 upon 2 square. On solving, we will get minus 328. Put n equals to 3. On solving, minus 1312 upon 3 square, we will get the answer minus 145.8. So from here we can conclude that this energy difference is not same. First energy level is having quite high energy, that is minus 1312. Second energy is 328. Third shell is having energy 145. And fourth shell is having energy 82. So there is not constant spacing between the lines. So this graph can easily explain that the energy differences between various shells is not uniform. So that's why energy levels are not equally spaced. Now the frequency and wave number associated with the absorption and emission of the photon can be calculated as mu equals to delta E upon H, or RH is RH 1 upon Ni square minus 1 upon Nf square. Or when we substitute the value for delta E, it is 2.18 into 10 to the power minus 18 joules. and H is a Planck's constant, 6.626 into 10 raised to power minus 34 joule second. So on solving, we get the equation nu is equal to 3.29 10 raised to the power 15 1 upon Ni square minus 1 upon Nf square, and the unit will be hertz, since it's a unit of frequency per second or hertz. Similarly, wave number can also be calculated using the formula 1.09677 into 10 raised to the power 7 1 upon Ni square minus 1 upon Nf square meter inverse, where Nf, when Nf is greater than Ni, means the term in the bracket is positive and energy is absorbed. But when Ni is greater than Nf, delta E will come out to be negative and energy is released. Let us now talk about achievements of Bohr's model of atom. Means Bohr was able to explain the stability of an atom. According to Bohr, electron present in a particular energy will not lose any energy while revolving in the same shell. It only emits or absorbs energy when it jumps either from higher shell to the lower shell or from lower shell to the higher shell. Number 2, it has been used to derive Bohr's formula, that is delta E is equal to 2.18 into 10 raised to power minus 18 joules 1 upon 2 square minus 1 upon Nf square. Since for Bohr's formula Ni is fixed, that is 2. Number 3, it helps in calculating the energy of electron in hydrogen and hydrogen-like species, that is En is equal to minus 1312 into Z square upon N square kilojoules per mole, or minus 1.312 into 10 raised to power 6 Z square upon N square joules per mole. Number 4, it helps in the calculation of number of spectral lines when an electron jumps from any higher shell to the lower shell. Now the number of spectral lines can be calculated using the formula N2 minus N1. N2 minus N1 plus 1 upon 2. For example, if an electron jumps from fourth shell to the first shell, total number of spectral lines expected here are 4 minus 1, bracket closed, again bracket starts, 4 minus 1 plus 1 upon 2. That means the answer will be 3 multiplied by 4 upon 2, that is 6 lines will be present in the spectrum when an electron jumps from fourth shell to the first shell. Next is, it can also explain the large number of spectral lines in the spectrum. Now in case of hydrogen, there is only one electron. So we think and we assume that if there is only one electron, that one electron will be absorbing energy, will go to higher level, and when it will come back, it will emit only one line, one radiation, means radiations of only one wavelength. But actually we get 5 series of lines, and each series having large number of lines. So why we are getting large number of lines in the hydrogen spectrum? It is because each hydrogen atom which is excited or which is formed as a result of the dissociation of hydrogen molecule in the discharge tube has one electron. And when the hydrogen gas was ionized, hydrogen atoms were separated, the electrons, they were moved or they were jumped to the different states. So electrons, they absorb different amount of energy, hence they are excited to different higher energy states. Now depending upon the energy absorbed, when they come back, they will emit the energy. So they will be emitting different energies. It is not like that if all the electrons have been jumped to the 7th shell, they will all immediately come to the first shell. No. Maybe the electron who has jumped to the 7th shell will first of all come to the 6th, then will jump to the 5th, then from 5th to directly first, or from 5th to the fourth level or from fifth to the second level. So accordingly, different electrons will be emitting different amount of energies. Hence we get different number of lines, because electrons will jump back to the ground state in different ways. All will not follow the same route. So that's why we get large number of lines in the spectrum. Next is limitations of Bohr's model. So Bohr's model has got some limitations. Number one, it fails to explain the finer details of the hydrogen atom spectrum observed by spectroscopic techniques. Means it is unable to explain the spectrum of atoms other than hydrogen also. It also fails to explain the concept of Zeeman and Stark effect. Zeeman effect means splitting of the lines in the presence of external magnetic field, and splitting of the main line into the fine lines in the presence of electric field is called Stark effect. Next limitation is it does not explain the ability of atoms to form molecules with chemical bonds. So these are few limitations of Bohr's model. Now when we come across numericals, we are usually given a numerical, that is calculate the wavelength of or energy of two longest wavelength lines, let's say in the Lyman series of hydrogen spectrum. So remember, longest wavelength means if n1 equals to 1, then n2 has to be 2. Longest wavelength line will be determined when n2 value will be minimum, n2 or nf value will be minimum, then the line will be of longest wavelength and of minimum energy. Number 2, if we want to calculate the energy of ionization, then n2 or nf has to be filled as infinity. n2 and nf should be infinity in case we want to find out the ionization energy.